Hello everyone, and welcome to today's presentation. I'm excited to be with you as we explore the essentials of VRF refrigerant piping brazing. On this first slide, you'll see the title, VRF refrigerant piping brazing. We'll be covering what brazing is, how it works with copper and silver-based alloys, and why it's important for reliable HVAC systems. So, let's get started and dive into the world of brazing techniques and their role in VRF systems. So let's explore what brazing actually is. Essentially, it's a process used to bond metals together, and it involves applying heat along with a filler metal, which is often an alloy. Now, what's important to note is that this heating occurs at temperatures above 840 degrees Fahrenheit or 440 degrees Celsius. But here's the key point. These temperatures are still below the melting point of the metals we're joining. By heating the metals and the filler alloy to this specific range, we enable the alloy to melt without melting the base metals themselves. This is crucial because it allows for a strong and precise bond without damaging the parts. Another interesting aspect of brazing is how the process works in practice. As the alloy melts, it's drawn into the joint through capillary action, kind of like how a wick draws up liquid. This capillary action helps create a tight, reliable bond between the metals. Throughout this presentation, you'll see how understanding these fundamental processes is essential for mastering various metal joining techniques. Brazing, in particular, offers a versatile and efficient method for creating strong joints in many applications. Today, let's take a closer look at the various types of brazed joints and what makes each one unique. When it comes to best practices, choosing the right joint type is crucial for ensuring a strong and reliable bond. First, we have the horizontal or flat flow joint. This is often used when the surfaces are parallel and flat, making it easier to control the flow of the filler metal. It's a straightforward approach that works well for many applications. Next, there's the vertical upflow joint. In this setup, the joint is oriented so that the filler metal is fed from the bottom upwards. This method helps promote proper flow and can reduce the risk of trapping impurities or air pockets. Then we have the vertical downflow joint. Here, the filler metal is introduced from the top and flows downward. This can be advantageous when working with certain materials or in specific assembly scenarios, as it can help achieve a cleaner, more controlled bond. Overall, understanding these different joint types allows us to optimize the brazing process, ensuring strength, durability, and quality in our final products. Connecting these points back to our theme, selecting the appropriate joint type is a key step toward achieving the best possible results in brazing. Now, let's talk about how capillary action works in this process. Essentially, capillary action is the force created by the surface tension of the alloy. This force pulls and spreads the molten filler metal into the gaps between the metals we're joining. It's like the alloy is being drawn into the space naturally. The role of heat here is crucial because it helps in drawing the alloy into these small spaces. When we apply heat, it makes the alloy more fluid and easier to move into the joint. So in summary, the alloy's surface tension, combined with the heat, pulls the filler material toward the heat source, filling the gap efficiently. This process ensures a strong, well-formed joint. Now, let's walk through the 6 essential steps of brazing, which is a critical process for creating strong, reliable joints. First, we need to ensure a good fit and proper clearance between the parts. This is important because if the parts don't fit well, the brazing material won't bond properly. Next, cleaning the metals is crucial, removing any dirt, oil, or oxidation that could interfere with the process. Clean surfaces ensure better adhesion and a stronger joint. Then comes assembly for brazing, where you position the parts carefully to maintain proper alignment. After that, fluxing the parts is necessary. Applying flux helps prevent oxidation during heating and improves the flow of the molten filler metal. Moving on to the actual brazing step, where you heat the assembly until the filler metal melts and bonds the parts together. This is the core of the process, and temperature control here is key to a successful joint. Finally, once the brazing is complete, cleaning the finished brazed part is essential. Removing any residual flux or excess filler ensures the joint is clean, durable, and ready for use. These 6 steps, when followed carefully, help us achieve high-quality brazed joints that meet the necessary standards for strength and reliability. Let's take a closer look at what makes a good fit and proper clearance. When we're talking about clearance, we're typically referring to a gap of about 1/4 inch, which is roughly 6.35 millimeters. The actual clearance at room temperature should be between 0.002 inches and 0.005 inches, or about 0.5 millimeters to 0.127 millimeters. This range is crucial because it ensures there's enough space for proper installation and function without causing excessive looseness. Additionally, the insertion depth should be a minimum of 1/4 inch or 6.35 millimeters. This depth helps guarantee that the parts are securely fitted and properly aligned. Overall, maintaining these precise measurements and clearances is key to ensuring safety, performance, and longevity of the assembly. It's all about finding that perfect balance to make sure everything fits just right without being too tight or too loose. All right, let's talk about 2 common issues we often encounter: being too tight and being too loose. When something is too tight, it can cause stress or damage, whether we're talking about processes, relationships, or even physical systems. It's like over-tightening a screw eventually. It might strip or break. On the other hand, being too loose means things aren't secure enough, which can lead to inefficiencies or failures. Think of it like a loose bolt. It's not holding things together properly. The key here is finding that balance, that optimal point where everything functions smoothly without unnecessary strain or risk. This concept ties directly into our overall theme of effective management and design, getting it just right, not too tight, not too loose, but perfectly calibrated for success. Capillary action will only work effectively if the surfaces of the metals you're brazing are completely clean. This means you need to start by removing any dirt, oil, grease, or even tape adhesive that might be present. These contaminants can block the capillary flow and prevent the solder from properly bonding. Next, you'll want to get rid of scale, rust, and oxides using a Scotch-Brite pad or similar abrasive. This step is crucial because these layers can also interfere with the bonding process. It's very important to remember, though, that you shouldn't allow these contaminants to enter inside the parts you're cleaning. Once you've prepared the surfaces, use the parts immediately to prevent recontamination. Proper cleaning and handling are key to ensuring a strong, reliable brazed joint. This is all about making sure the capillary action can do its job by providing a clean, unobstructed surface for the filler metal to flow and bond effectively. Let's take a closer look at how oxides influence alloy distribution during welding. As you can see in Figure 2, when we use flux, it plays a crucial role in preventing the formation of oxides on the surface of the base metal. This is important because oxides can interfere with the bonding process. By stopping oxide formation, flux allows the filler metal to properly wet the base metal, leading to a stronger and more uniform bond. Now, if we look at Figure 1, without flux, surface oxides tend to prevent the filler metal from wetting the base metal. Instead of spreading out, the alloy beads up on top of these oxides, which can create weak points or even defects in the weld. So, the key takeaway here is that controlling oxide formation is essential for achieving a good weld. Flux helps us do that by removing or preventing oxides, ensuring that the filler metal can wet and bond with the base metal effectively. This concept ties back to the overall theme of optimizing weld quality through proper control of surface chemistry and alloy distribution. When assembling and supporting the braze joint, it's best to position the joints in a vertical down orientation whenever possible. This helps ensure proper flow of the alloy and reduces the risk of defects. It's also important that the joints are straight, carefully aligned, and supported adequately throughout the braze process. Proper support prevents movement that could compromise the quality of the joint. Once the brazing is complete, you must avoid moving the parts until the alloy has fully set. Moving them too soon can cause cracks or leaks, which we definitely want to avoid. When working with subassemblies, fixturing is critical. Using fixtures not only provides the right alignment and ensures a proper fit-up, but also protects valves and other sensitive parts from damage during assembly. Additionally, providing a nitrogen environment during assembly is key. Nitrogen helps prevent oxidation and contamination, leading to a cleaner, stronger joint. Overall, these practices, proper orientation, alignment, support, secure fixturing, and controlling the environment, are all vital to producing high-quality braze joints that will perform reliably in service. When performing brazing near sensitive parts like valves, distributors, or any other critical joints, it's essential to protect those components from heat damage or potential leaks. The key is to isolate or shield these parts effectively during the process. One simple yet effective method is wrapping the area with a dripping wet shop cloth, which helps absorb heat and prevent it from reaching delicate parts. In addition to wrapping, there are other methods to safeguard these sensitive components. Heat sinks are used to draw heat away from critical areas, helping to keep them cool during the brazing process. Heat shields act as barriers, reflecting or absorbing heat to prevent damage. Wet rags, like the shop cloth, serve as a cooling barrier by maintaining moisture, which absorbs heat and provides protection. Overall, protecting sensitive parts isn't just about preventing damage. It's about ensuring the integrity of the entire system. When we take these precautions seriously, we minimize the risk of leaks or failures that could happen if heat causes damage. It's a crucial step in ensuring a safe, effective, and professional brazing operation. Let's take a closer look at nitrogen purge. On the left side, you can see the debris. These are oxides that formed on the sample left tube. This happened because there was no nitrogen purge during the process. Oxide formation is a common issue when metals are exposed to air at high temperatures, which can compromise the quality of the brazing. Now, on the right side, you see the right tube that was properly purged with nitrogen. This proper purging prevents oxides from forming during the brazing operation, ensuring a cleaner, stronger joint. This highlights a crucial point. All tubing assemblies must be purged with nitrogen during brazing. Doing so is essential for maintaining the integrity of the assembly and preventing defects that could lead to failures down the line. So, in the context of our overall theme, precision and quality in manufacturing, using nitrogen purging is a simple yet vital step to achieve optimal results. When setting up for brazing, it's important to pay close attention to your gauges. You'll notice on the slide that the oxygen gauge should be set at 20 psi, which is the standard working pressure. The gas gauge, on the other hand, should be at 10 psi. These settings are crucial because they ensure you have the right amount of pressure for a safe and effective brazing process. It's also key to remember that the maximum fuel gas pressure should never go above 15 psi. Exceeding this limit can be dangerous and may compromise safety. Another important point is that gauges should always be in good condition, never damaged or cracked, because you need to be able to clearly read the pressure settings at all times. As brazers, having accurate, easily readable gauges helps us maintain control and ensure safety throughout the process. So always double-check your gauges before starting, and make sure they're correctly set and in good shape. This small step makes a big difference in keeping your work safe and efficient. When starting your shift, it's important to first turn both the fuel gas and oxygen valves to the off position. This ensures safety before handling the torch. Then, lift the torch from the gas saver carefully. Next, open the gas valve on the torch just half a turn and light the torch using a striker. When opening the oxygen valve, do it slowly until you see a defined inner cone, often called a feather, forming in the flame. Remember, never use a match or lighter to ignite a brazing torch, as this can be dangerous. Proper lighting is essential for safe and effective operation, and these steps help ensure everything is done correctly from the start. LPG, or liquefied petroleum gas, plays a significant role in the energy landscape. It's a versatile fuel that's used worldwide for heating, cooking, and even as an alternative fuel for vehicles. One of the key advantages of LPG is its high energy density, which makes it efficient and easy to transport. It's stored in pressurized tanks, allowing it to be delivered to areas without access to natural gas pipelines. LPG is also considered a cleaner burning fuel compared to other fossil fuels like coal or oil, contributing to lower emissions when used properly. This makes it an attractive option in the transition toward more sustainable energy solutions. Throughout our discussion today, understanding the role of LPG helps us see how diverse energy sources can complement each other, especially in regions where infrastructure for natural gas isn't fully developed yet. It's an important piece of the broader energy puzzle, balancing convenience, efficiency, and environmental considerations. Let's take a closer look at acetylene. Acetylene is a highly flammable hydrocarbon gas, and it's widely used in welding and cutting metals because of its intense flame temperature. One of the key points to remember is that acetylene is quite unstable under certain conditions, especially when stored improperly or exposed to high pressure. That's why specialized cylinders and safety protocols are essential when handling it. Another important concept is that acetylene's chemical properties make it ideal for creating a very hot flame, which is why it's preferred in many industrial applications. But because of its flammability, understanding its behavior and storage requirements is crucial to prevent accidents. Overall, acetylene plays a vital role in various industries, and being aware of its properties helps us use it safely and effectively, tying into our larger discussion on industrial gases and safety practices. As the ratio of oxygen to fuel gas changes, the nature of the flame and its applications also change. Let's start with the neutral flame. It has no feather, and the inner cone is a light blue color. This type of flame is actually the best choice for brazing copper joints because it provides a clean, stable heat without introducing additional oxidation. Next, we have the reducing flame. You'll notice it has a small feather and a brilliant blue inner cone. This flame is ideal for brazing large steel joints because it contains a higher amount of fuel gas, which produces a slightly different heat profile. Finally, there's the oxidizing flame. It doesn't have a feather, and its inner cone is a small, light blue color. The cone is noticeably smaller compared to the neutral and reducing flames. It's important to note that this type of flame should not be used because it has a high oxygen content, which can cause oxidation and damage the materials you're working with. Understanding these differences helps us select the right flame for each specific application, ensuring safety, efficiency, and the best quality work. Let's talk about the correct brazing temperature. When you're heating copper, you'll notice it reaches a dull red color. That's actually the signal that you've hit the right brazing temperature. It's an important visual cue to ensure proper bonding. Now, here's a critical point to remember. If the copper turns cherry red, that means it's overheated. Overheating can compromise the integrity of the joint and weaken the metal. So, always watch for that dull red glow and avoid pushing it into the cherry red range. Keeping the right temperature is key to achieving a strong, reliable brazed connection. All right, let's talk about what happens when brass gets overheated during brazing. When you're heating the brass, a key indicator to watch for is the color change. When the brass turns dark red, that's your cue that you've reached the correct brazing temperature. It's a crucial visual cue that the metal is hot enough to allow proper flow of the filler material and create a strong bond. However, if you see the brass turn bright red, that's a sign you've gone too far. Bright red indicates the brass is overheated and is close to melting. Overheating can compromise the integrity of your joint and lead to failures down the line. So the main takeaway here is to carefully observe the color change. Recognizing when the brass turns dark red versus bright red helps ensure you're applying the right temperature, which is essential for a strong, reliable brazed joint. This ties back to our overall theme of precision and proper technique in brazing. Getting the temperature just right makes all the difference. Overheated. When you're brazing, it's crucial to get the temperature just right. Correct braze temperature is key to a strong, reliable joint. Now, a good rule of thumb is to watch the steel itself. When the steel just starts to turn dark red, you've reached the right temperature for brazing. This color change is a clear visual indicator that the metal is hot enough to flow the filler metal without overheating. Overheating can cause problems like weakening the metal or burning the flux, which we definitely want to avoid. So, always keep an eye on that color change. It's a simple but effective way to ensure you're at the correct temperature and maintaining quality throughout your process. When heating the parts to be brazed, start by focusing on the inserted, or male, part. Heat the area about 1/2 inch to 1 inch from the outside edge. It's important to do this first because it helps ensure even heat transfer between the parts. As you bring both parts up to brazing temperature, aim for as even a heating process as possible. This helps prevent any weak spots or stresses in the joint. To maintain a consistent temperature, use a rolling and sweeping motion with your torch. This technique allows the heat to be evenly distributed across the surfaces, leading to a stronger, more reliable joint. Remember, controlling the heat carefully is crucial for a successful brazing process, and this step ties directly into the overall goal of creating durable, high-quality joints. Let's take a closer look at the flat or horizontal position first. This is where we start the heating process. It's important to begin here to ensure even heat distribution. When applying the alloy, make sure to do it at this initial stage, right at the start of heating. Now, moving on to the female and male parts, these are the components you'll be joining. Proper placement and preparation are crucial for a strong, reliable bond. Next, we have the vertical up position. This is another key step. Here, you'll apply the alloy again, making sure it's exactly where it needs to be. Then, we proceed to the vertical down position, which is considered the best practice. This position helps achieve optimal bonding quality. At this stage, apply the alloy carefully, following the same principles as before. Remember, always start heating at the designated point, marked with an asterisk. The goal is to ensure uniform heating and the best possible fit between the female and male parts. Having a clear understanding of these positional changes and applying the alloy correctly at each stage will significantly improve the integrity of the joint. These steps are part of the overall process to ensure precision and strength in our assembly. Now, let's talk about how to properly apply alloy during brazing. For larger tubes, you want to lay the alloy along the joint itself. This ensures that the alloy flows evenly and creates a strong bond. When you're working with smaller diameter tubes, the approach is a bit different. You should apply the alloy at a single point and then move it around the tube to spread the material evenly. It's important to preheat the alloy first. Hold it near the outer flame of your torch, not directly in the flame, to gently warm it up. This preheating helps the alloy melt smoothly when you start brazing. Remember, only start applying the alloy once you've reached the proper brazing temperature. This is critical for a good, strong joint. When you do begin applying the alloy, use the heat of the tube itself to melt it. Do not use the flame directly to melt the alloy. That can cause contamination or poor flow. Instead, rely on the heat of the tube to draw the alloy into the entire joint through capillary action. This ensures a complete and reliable bond. So, in summary, carefully position your alloy, preheat it properly, wait for the right temperature, and use the heat of the tube to melt and draw in the alloy. This process is all about control and patience to achieve the best results. All right, let's take a closer look at how capillary action works in this process. As you can see, we have the alloy and the heat source. When the joint is made correctly, the alloy should settle at the bottom of the inside tube, filling the space between the inside and outside tubes all the way around the joint. It's important that the alloy fully fills this area but doesn't overflow, ensuring a proper seal. Now, here, the key point. The alloy is actually attracted to the hottest area. This means that when we heat the joint, the alloy moves toward the heat source, effectively filling the joint through capillary action. This makes the process both efficient and reliable, especially when you understand how the alloy's attraction to heat helps it flow into every nook and cranny of the joint. So, in essence, proper heating guides the alloy to where it's needed most, ensuring a strong, even bond around the entire joint. Now, let's take a look at some examples of unacceptable braze joints. First, we have dripping alloy, which indicates that the alloy has not been applied properly and is running or dripping down the joint. This can compromise the integrity of the connection and lead to leaks or failures later on. Next, we see a crooked joint, where the alignment is off. Proper alignment is crucial for a strong, reliable bond. so a crooked joint can cause stress concentrations and reduce the overall strength. Finally, there's the issue of applying too much alloy and overheating the copper tubing. Overheating can weaken the copper and create weak spots, while excess alloy can cause unnecessary buildup and potential blockages. These examples highlight the importance of proper technique and attention to detail in brazing, ensuring we meet safety and quality standards across all our work. Now, let's take a look at some examples of acceptable braze joints. As you can see, these examples demonstrate proper technique and good craftsmanship. The key points to observe here are the consistent, smooth bead lines and proper fit-up, which are essential for ensuring a strong and reliable joint. Remember, a well-executed braze joint not only meets the technical standards, but also contributes to the overall integrity of the assembly. These examples highlight what we should aim for in our work: precision, cleanliness, and attention to detail. When we follow these principles, we can be confident in the quality and durability of our brazed connections.